Hello students, welcome to our fourth in our series of video here on Taylor series and Taylor polynomials. And in the last couple videos we tried three different attempts to find a good polynomial that will approximate the sine function. And I think we've arrived to a point now where we can talk about Taylor and his general idea. So his general idea is, again, we're going to use g of x to approximate f of x. Okay. And our special point here is a. Okay. And Taylor said, well, why don't we just do this? We're going to use g of x is equal to f of a plus f prime of a times x minus a. We know that by doing this, we get g of x to agree with f of x up to the first derivative. If we add another term, it's going to be the second derivative of x at a times x minus a quantity squared divided by 2, and that's going to get the function to agree, the function g to agree with the function f at a up to the second derivative. And if we want more accuracy, we'll take the third derivative of f at a times x minus a to the third power. And this part's a little bit different. You're going to divide it by 3 factorial, or 3 times 2 times 1. And in our trials and errors, we'll see that this factorial here is necessary, and it took Taylor a little bit of time to figure that out. And if we want another term, well, then that's just the fourth derivative at a times x minus a to the fourth power divided by 4 factorial, and so on. Okay, and we can generalize this. I mean, 2 is, technically 2 factorial. Okay, and this is really divided by 1 factorial, and this is also divided by 0 factorial, which happens to be 1. Okay, and so, he said, look, if you want more accuracy, calculate more terms. Okay? If you want more accuracy, all you have to do is calculate more terms. Okay? So let's put this to practice a little bit. Let's use 4 terms now to estimate the value of sine of 2 pi over 13, and we can compare this to the value from your calculator. Okay, so let's see, 4 terms. So the first term is going to be, and we're going to use a number. Let's use pi over 6 again. Okay, because pi over 6 is close to 2 pi over 13. So our first term would, then let's write out some notes on the side. Okay, so f is sine, cosine is the first derivative, negative sine is the second derivative, negative cosine is the third derivative, and then the fourth derivative, we're back to sine again. So let's see, the first term is going to be f of a, which is, so g of x is equal to f of a, which is sine of pi over 6, which is 1/2, plus the derivative of f, so cosine of x at pi over 6, so root 3 over 2 times x minus a, which is pi over 6. So this is our special point, right? Plus the second derivative, so negative sine at pi over 6, or negative 1/2, times x minus pi over 6 squared times 1/2. Okay, that division by 2. So we have 1 term, 2 terms, 3 terms, plus the third derivative, which is negative cosine, or negative root 3 over 2 of x minus pi over 6 raised to the third power times 1 over 3 factorial, which is 1 over 6. And according to Mr. Taylor, this equation here is a very good approximation of the actual value of sine of 2 pi over 13. So g of 2 pi over 13, and I'm going to take out my calculator and let it do this, is equal to, so we're going to take 2 pi over 13 and plug this into these values for x, okay, and see what we get. Okay, so I got this mess here entered into my TI-83 calculator, and then if I substitute in 2 pi over 13, that's the result that I get. And if you compare this to the actual, or not really actual, but the sine function in your calculator, you get almost the same thing. Okay, and notice here that pi over 6 is pretty close to 2 pi over 13, but we can also try this for other values as well. So let's see, even if I try something like pi over 4, which is not that close, it's still pretty darn close to the real value of the sine function. And just to bear in mind here, y1 here in my calculator is a polynomial. Okay, so what we've done so far is we've created a polynomial that does a pretty good job of approximating the sine function for some values, more than one value, but maybe not all values. And we can let's see. Let's try some other ones. Sine of pi is 0. If I try my equation, sine of pi, okay. Now you can see that at pi it gets pretty far off, but perhaps pi over 2 and the actual pi over 2, which is 1, right? These two are getting pretty close. Okay, so this function here is not perfect, but it does a pretty good job from 0 up to pi over 2. Okay? And, well, the beautiful thing and the great improvement in Taylor's polynomial is that if you want more accuracy, you just calculate more terms. We only did 4 terms here, and we were able to get some pretty good results. If you want to get more accurate, well, you just calculate more terms. Okay? So, before I sign off here on this particular video, I wanted to show you the summation for this. So this is the summation symbol. So g of x is equal to f, we're going to use k here, our kth derivative of a times x minus a raised to the kth power, all divided by k factorial. And we're going to start out from k equals 0 to n, okay, where this is terms, however many terms that you wish. Okay, and this is using g to approximate f, okay, with a as our special point. Okay. So hopefully you get some sense here of how we were able to use a polynomial to estimate the sine function. Oh, I just realized I forgot to actually write down this value. So this is 0.464723118, and then the calculator, the TI-83 that I have, actually gives me 0.464723172. Okay, so they agree for that many decimal places. Using 4 terms, I get a polynomial that behaves like the sine function up to this many decimal places. So that's pretty good. And I know we have calculators now, but actually this is what your calculator is doing. It just uses more terms and gets a more accurate result. Thank you for watching. Have a wonderful day. Be sure to watch the rest of these videos.